Yay. Sorry. Okay, I think Aaron, you said you had a question from
31.
Okay, 31. I'm glad to go over as many as you guys want before we move on to some newer stuff here. Okay, so 31 is just it's from ground level. Sorry. So cannonball shot from ground level. And they don't tell us what the initial velocity is, so let's call it V. And the only information we have, well, we know eventually it's going to go to its max height. Okay. But they give us this information that when it's 30 meters above the ground, it's traveling 18 meters per second. So is everyone okay with the way I drew the picture? Okay, so then all we got to do is quantify the energy here. Say how much energy can we account for right here, and then solve how high does it go and how fast is it going. We're just going to set the energy equal to those two moments. Now you'll notice this question, what do they not give us? The mass. So you got to be a little clever here and be like, well, okay, I guess I'll just write for this moment in time, the total energy is 1/2 mv squared plus mg, what's the h, 30. Does that make sense? That's the total energy. If you really want to, you can just make up a mass. Just make a note of that. Say, I'm gonna make up the mass for this question. But anyway, let's watch what happens. Let's solve the first question. What was the initial velocity? So this total energy has to be equal to the total energy down here, which is 1/2 mv squared. Everyone cool with that? So then what happens? If you divide both sides by m, it drops out. And so now with my calculator, I'm going to type in 1/2 times 18 squared plus 9.8 times 30. So this number on the left side should be 4. That's a nice number, 456. Look at that. That's pretty neato. And now from there, it's pretty straightforward, right? You got to double both sides, so times 2, and then take the square root. And I'm getting 30.2. Oh wait, did I make a mistake here? Where did I mess up? Oh no, sorry. I got confused because I was like 30. I thought for a second I thought they said that they left the cannon at 30, but no. Just a numerical coincidence. So numerical coincidence that the initial velocity ends up being almost the same number, not different units, of course, but almost the same number as 30. It's kind of weird. Okay. Are we cool with that? Makes sense? And then let's figure out how high does it go? It's red, I guess. How high does it go? Well, same calculation. Does it make sense how if I wrote out the same thing, except like same left side, but if the right side instead, I wrote mg times h max, then my calculation, after I cancel the m's, right? Then I would just have, from there, I would just have 4, 5, 6 equals g times h max. Let me know if that's confusing. I can write out the whole thing if you'd like. But. Good morning.
Hey, is Kate here?
That makes sense? So in this case, it would just be that same number as before, divided by 9.8. So 456 divided by 9.8, you're going to get 4086. which makes good sense, right? It was going 30 meters per second, or sorry, it was 30 meters in the air. It was going 18 meters per second, so it stands to reason that would have gained a bit more elevation, but not a ton more, so it wasn't going that fast. 46.5. All right, are there any more questions from this problem set? I wanted to pick one, but my pages got all knocked out of order. So it was the one where how high does the ramp have to be to loop-de-loop around? Where's my loop-de-loop toy? Where's that thing? Oh, there it is. All my papers got like completely scrambled. Certainly no fault of my own. Some mysterious force must have done it while I wasn't looking. Anyway. We're going to answer this question, so can someone find it and just tell me where it is? Okay.
One of those.
It's, we'll do 57 and like 60. So the question we're going to answer today is how fast do you have to be going to go around the loop-de-loop? That makes sense? So there's two ways you can phrase that. One is what if you're approaching the loop-de-loop from the ground, from ground level, how fast do you have to be going? The other way you can phrase the question is how far up the ramp would I have to start this thing? Like let's try this. Is this going to work? Probably. No, it didn't work. If I go this high, it works. And you could, through trial and error, for a given loop, you could be like, oh, maybe here. And I think I heard him leave the track there. So anyway, you get the idea, right? So we're going to calculate theoretically how, assuming frictionless, no air resistance, how high up, can you quantify that? How high up would you have to start to get around? So this is, of course, the maybe the most overly simplified version of designing a roller coaster you can come up with. In practice, those aren't actually circular loops, but they're sort of teardrop shaped. Anyway. What? What?
I like them.
Oh, I like them too. Yeah, I love roller coasters. They're great. I really want to go to that big one in Pennsylvania one day. You guys ever heard about that? It's called Kingda Ka, I think, and it's like 450 feet tall. I rode the Superman ride, which I thought was insanely tall. They crank you up to this thing, and you're just like, I'm so high up. But that was only like 200 and I want to say it's like 220 feet or something, or 215. This one, Kingda Ka, is twice as tall. It'd be amazing. Anyway.
They have some good ones in Carolyn, North Carolina. They have like a really fast one that goes like 90 or something.
That's awesome. What, Kate, you like roller coasters?
It's not that I don't like roller coasters, but the one Panic Plunge at Silverwood just can't do it.
That's a fun one. Really sad. It's really sad I can't do the spinning one anymore because I am become boomer. As a kid, I used to love those rides. I was the more twisty and crazy, the better. And now, the last time I got on it, I got pretty sick. It's made me nauseous because I guess I'm too old for it now. It sucks. Sad. Big sad. So this is the first one we're going to do. Is you got, this could be a frictionless block or a card. Let me go grab a black marker. I'll be our beats. So guys, well, look at my marker here. Try to figure out something real quick, which is, you might remember this result. Because ultimately we're going to ask, correct me if I'm wrong here, we're asking how, thanks. Yeah, this is 57. Oh yeah, is the block going fast enough to complete the loop without falling off and explode? So using Newton's law, you got to go back to your Newton's law idea. How fast does he have to be good? What's the minimum speed he has to have up here in order to not fall off? That's the first thing we want to ask, okay? Let me go grab my marker.
I didn't make stuff up. I didn't make stuff up.
That's from that.
All right. So, what's the radius of the loop on this one? 6. Okay, so if the radius is 6 meters, then what you can do is say, for the minimum speed, there's just this one force. Where does the force come from? Gravity. So gravity, if you whip around this loop, then the track pushes you and you feel some weight. If you're going the minimum speed allowable, you'd feel weightless at this moment. So what you'd say is that this vector would just be mg. And so if you wrote F net equals ma, so net force would just be your mg, and your acceleration would be v squared over r. Does that all ring a bell? Okay, and so what you get is that. So you get your velocity has to be the square root of 6g. Does that maybe ring a bell? Remember square root of GR? That was the famous result for that question. So let's get a decimal here. What does this come out to be? I'm going to call it v top.
7.67.
Do you guys, well, answer this one. Do you understand what we just calculated? This is the minimum speed that you got to have at the top to not fall off the loop. So let's do our energy calculation, and if we find out that he's only going 5 meters per second, no, he's going to fall off. But if he's going faster than this, he'll be fine. That make sense? So let's do the calculation. How fast is he going down here?
18 meters.
18 meters per
Oh,
second.
he's got it under control.
Think so?
Yeah.
How tall, how much height does he have at the top of the loop? 12 meters. Okay. So let's do the calculation. Total energy is 1/2 mv squared. And then, this is. What's up? Oh God. Don't look over here. Nope, it's falling off. It's falling apart. I was just trying to make it look better, and I made it worse. What am I doing? I don't know. I don't know what I'm doing. Okay, hopefully that helped for the millions of Twitch fans. Okay. They give you the mass? Okay, so we put the mass in. What's the mass?
10.
Okay. And then at the top of the ramp, right, he's going to have potential energy, which is mgh plus 1/2 m. That all makes sense, right? Sorry, I kind of ran out of room. Had to think of 2 lines, but go ahead and solve that for v and see what you get. So this side, you just calculate that. You subtract that away. I don't know. Test your calculator kung fu there. I'm gonna go type this in, so 5 times 18 squared. I'm gonna subtract this number, so I'm gonna type in minus 10 times 9.8 times 12. So I have 444 on the left side now after subtracting that. Then I divide by 5, and I take the square root, and I get 9.4 roughly. 9.42 if you want to go 2 decimal places. Okay, so is that better than that? Or maybe I shouldn't say better, but it's faster. So, so therefore, now I feel kind of silly for labeling this V top. I should have probably called this V min. Meaning that's the minimum allowable velocity at the top without falling off. We exceeded that, so we're gonna be fine. We're gonna make it through the loop. So the next problem is similar to this. I think the next one is set up so that he's gonna fall off. So you just do the same calculation, make sure you understand that process. I think you're gonna find that, yeah, whatever the minimum velocity happens to be for that, you end up not exceeding that, so. Okay, so I wanted to also go over the one that's gonna ask us the same setup, so it's the same loop-to-loop. All right. What we're gonna answer is how fast do you have to be going here in order to make it around the loop? So is that like 59? Is that, or is it? We'll do 60 with just the symbols. How about that? Sound good? Okay. Thanks. So, and I'm going to call this V. I guess I'll just call it. We'll just call it V. Just know that this one's called V. We're going to solve for V. So if the circle has a radius of r, we've already done this calculation, right? What is the minimum? What does the speed have to be up here for him to stay in the loop? Yeah, so the velocity at the top is the square root of g times r, square root of GER. We okay with that? Okay, so we already calculated that. We can use that again. So now what we do is we say, what does this have to be in order to achieve this? Well, it's going to slow down, right?
Yeah. Oh, sorry.
So that's the trick. That's the hard part is, let's say you do the calculation and you say, well, you'd have to be going 20 meters per second at the top to make it around. Well, then you got to be going faster than 20 meters per second here to make that work, right? Because you're going to slow down as you increase in height. So what you do is it's the same process we always do. We just calculate the total energy. Total energy down here would be 1/2 mv squared. All right. And then let's quantify the total energy up here. Considering that his height, what's his height? 2r. So let's write his kinetic plus potential. His kinetic is 1/2 mass. Is everyone cool with how I did that? 1/2 mv squared plus, let's get his mgh. mgh. Are we okay with that? Okay, so first thing that's going to happen, let's cancel those masses, and then let's multiply both sides by 2. So multiply by 2, you get, what do you get here? So multiply it by 2, it gets rid of the 1/2. And then what's the square root of GR squared is just GR, right? Plus, oh wait, because I remember I multiply both sides by 2, right? So what does this end up actually being? Will be, yes, it's 2 times G times R, then doubled. Are we still okay with why it's being doubled? So I wanted to, yeah, what I'm doing, technically I'm going like this, I'm multiplying both sides by 2. So this guy got multiplied by 2. This guy gets multiplied by 2. 2 bananas times 2 makes 4 bananas. Okay, now 1 banana plus 4 banana make 5 banana. So amazingly, you don't see a root 5 come up too often, do you? Stuff, but. So, are we okay with that? Does that make sense? Isn't that a nice result? That's pretty neato. So now the last thing I wanted to talk about is the loop-de-loop problem. Okay, and I think for this one we'll just, is it 62 that just says what's the height that'll allow it to go around the loop?
Yeah, it's all variable.
Because we could certainly ask the question, you could just ask the question, if we drop it from this height, how much force is exerted on the object by the ramp at some given point? But I think this one, we're just asking directly, how high, thanks. What's the minimum height we can drop it from that'll get it around the loop safely? That long. So go ahead and try to set that up while I erase here. So it's the same type of idea. It's just that instead of just starting with some velocity v, think of it as starting with some potential energy, mgh, right? You're going to use the GR idea. So starting with mgh, solve for h, that'll allow you to have this at the top of the ramp. Okay. Here's the ground. Here's the loop-de-loop. Here's the ramp. Okay. What should I do? What should I write for his energy here? MGH. So he starts off with MGH. And then we know that eventually he's going to come down the ramp, around the loop. But we're concerned with this moment right here. We're going to make an assumption that he's traveling how fast right there? What would be 0, by the way? There is an important quantity that would equal 0 here.
It's the normal force.
The normal force would be 0. Now remember, we calculated the velocity is going to be square root of GR. That comes from saying, let's assume that the normal force is 0, and then ask how fast does he have to be going at that moment in order for his normal force to be 0, and the answer to that is square root of GR. So now what we can do is, okay, assume he hit that target. Assume that that's going to be his speed when he's traveling through the top of the loop. So let's write his energy then here. His energy here would be 1/2 mg g squared, right? Plus mg h. And h, of course, there is its height is 2r, double the radius of the ramp. So we can probably see we're getting a bit of a different result here, but not super, super different. The m's cancel out like usual. And we're going to end up dividing by g. But first, let's look at this. I'm going to have half of a GR plus 2 GRs. How many GRs do we have then? 2.5 or 5 halves, however you want to think about that. Now here's a really weird thing. This is pretty surprising, I think. What else happens? And the G divides out. So what you get, weirdly, is that the height, that's an amazing result, I think. I mean, I would have thought, I don't know, if gravity was stronger, does that affect the answer? No. So it turns out if you had, on the moon, your roller coaster on the moon could have, I guess, the same, at least in the simplified design here, it wouldn't really matter how strong gravity is. The value of d doesn't matter. But yeah, you just need your height to be 2.5 times bigger than the radius. Okay, well. How do we feel? How are our feelies? Feelies good? Okay. All right, let's do the pendulum problem. We'll just. I guess I want to save some for you guys to try to figure out on your own, but I don't want there to be any. No, I don't. No, of course, that would be pointless. God.
It's really that way to work.
Okay. Well, these are not easy questions, so I want to at least give you an example from each type of question so that you're not lost. So, okay, so we'll do 65 here about quantifying this pendulum speed. And I've shown you guys pendulums before, right? So not like there's that much going on. It's just a thing attached to a string. You pull it, you let it go. You say, oh, you can answer questions like, how fast is this pendulum going? Okay. Or yours is on the right. Will that help? If I don't do it, that's a mirror image. How far back does this pendulum get pulled?
Theta, or 37.
37 degrees. Good. So here I'm going to draw its path here. So you could ask a question about this pendulum, which is, where does it get its speed from? Right? Gravity, sure. So if you want to be all physicsy about it, you'd be like, well, I could say that when I pulled the pendulum back, I had this force vector that did work on the pendulum, and that basically stored energy in the pendulum. Now, I don't want to do a bunch of mathematics or actually talk about a vector rotating and moving, so I'm just going to use height, right? So I guess what I'm trying to get at is you could say, well, here's my 0 position, And I can see that when you pull it back, the pendulum gains some height. Okay? So how long is the string here? 4 meters?
Yeah.
Okay. So then here's some geometry. What is that distance there?
4.
4. Everyone okay with that? What's a crinkling? Just pour them onto like a napkin or something. Okay. It was Aiden. The crinkle bandit. Okay. So this distance is 4 meters. Everyone okay with that?
Yeah.
And then let's find this distance. How will I calculate that? I gave you a little hinty there.
Triangle.
There's a right triangle. And then maybe take your head and go. There's a right triangle. They're giving you the hypotenuse and the angle. And then would this be the adjacent side or the opposite side? It's the adjacent. Adjacent goes with cosine. So this side length here is going to be 4 times the cosine of 37, which is, lost my calculator. About 3.2. Are we okay with that? Does that make sense? So therefore, how much height did the ball gain by being displaced? 0.8. So I'm gonna put a little box around that. That's gonna be the height. We sure there's no questions on that? Now, we just did something. Did we make the problem, would you say we made the problem a little simpler or a lot more simpler? A lot more simpler, right? Because now I can just go mgh 1/2 mv squared and I'll be done, right? It'll be easy peasy. Does that make sense?
Yeah.
So let's do the calculation. Up here, his energy is just mgh. His h is 0.8. And down here, he's got no height, so his energy is 1/2 mv squared. So the m's divide out, or you can keep them in there, it doesn't really matter. And then we can just take our trusty calculator and go, that. So g times 0.8, and then times 2, and you should get about 3.97. Does that make sense? So the principle is pretty simple. It's just before I showed you this, you might have been like, well, I really wish I could just do mgh equals 1/2 mv squared. That would make my life really easy. So that raises the secondary question of, okay, how do I figure out the height then? And that's a little bit of trig, a little bit of trigonometry, simple trig. Okay, let's just do one more from this. I guess we'll just wait for tomorrow to start the next thing. So at least then you'll have an example for every type of question. So there should be hopefully no confusion. You can work off the examples. The box. We're going to push Mr. Swiffer Sweeper. The broom.
Oh, I remember you.
The broom. The broom.
The box.
Huh?
The box.
There's another problem on there that talks about a ballistic pendulum, which is just, I have one, but it always like scares people because it makes a loud noise.
Oh, let's do it.
You want to do it?
Yeah.
Okay, let's remember where it is. I think it's this closet over here. I'll have to close the door.
Well, I can't say no to something that has the name ballistic.
Yeah.
It's a pretty low category. It's not.
Why don't you have it?
Okay, good.
Get a rock something.
But I am sad.
I gotta get the ball. Hold on.
I guess if we can do the ballistic pendulum problem too. And do the circle fever tomorrow. The hardest part is always getting the ball out of it. There's a ball stuck in there, yeah. There you just. It's really stuck in there. Oh my goodness. Might have to say this for tomorrow, guys. If I can get it out. Well, now. Oh. Okay. So the idea
is, okay, if anyone is watching this video, and you're wearing headphones, you should just take them out or mute it or something, because this thing is about to make a big loud noise. Also, it's basically I'm gonna shoot a ball. I'm gonna shoot a ball out of this cannon into this thing. It's gonna catch the ball and go pew. So, we should close the door too. It's not that loud, but it's loud enough that it can startle someone. Okay, let's put it right up to Julia. So basically the idea is, if you know about energy and you wanted to know how fast does this cannon shoot this ball, right? One way to do that is to shoot it into a little catcher and see how high does the catcher go back when you shoot it, right? And then do a little bit of mathematics to show, okay, if I can figure out the gain in height, then I can calculate how much speed it had at the beginning. Now, of course, where we're at in this class, we're right now, we don't have the tools, quote unquote, mathematical tools yet to account for the weight of the pendulum, but we're going to soon, once we talk about momentum. But for simplicity's sake, just assume that the catcher is massless. Assume that the ball is much heavier than the catcher. So I'm going to pull this back. Let's go all the way around. Let's go full power. I know. Get this thing out of my way so I can pull it. It's pretty strong, yeah.
That's not what
Oh, I didn't go all the way. There we go. Okay. It's all the way back. Ready? Spaghetti. Whee! There you go.
Oh, cool.
Huh?
So that was about.
That's loud enough. So you can see that we knocked it way back, like farther than we'd have to get the protractor out to see how far back we measured it. But there you go. This is kind of a cheapo one, but you get the idea, hopefully, right? Like you could then, yeah. Yeah, that'd be sweet. It'd be sweet to shoot an actual like cannonball into one, have like a big large scale. So anyway, let's just end class with this then. I'll show you then. Yeah, let's look at the math of 68. This is what we'll end on. 68 is just a reversal. you guys see how 68 is kind of like, you might go, wait, isn't 68 it's like just a mirror image of the last question we did, right? Because earlier I said, let's suppose we pull back the pendulum 37 degrees and release it. How fast is it going at the bottom? This one flips that around and says, suppose we know how fast was it going initially in order to generate this much displacement. So let's say that's theta. What's up?
I was just making sure it was 68, not 67.
Okay. So here's height 0. Here's the height of the ball. Same process. Do I call this one L or R? Is it L?
No.
L. So then how long is this piece right here? L cosine theta. And then how long is this whole distance here? That's just the length of the string. So then what's my height? Yeah. Everyone okay with that? So let's do the calculation then. He had a bunch of energy down here. Let's take 2 seconds. 1/2 mv squared, and he reached a height of this, so his potential energy was mgh. So solving this is pretty straightforward, right? Divide the m's out, multiply by 2, take a square root, and you're done. Cool beans? Okay. So complete a few of these problems for homework. We got to move on. I'm gonna cut several problems out of our final problem set to make it shorter.
Thank you.